is, like I said, a kind of a review, exploration of some right triangle work, information that you learned back in geometry, that's going to help lead us into our trig unit, which is unit 2. So it talks about, you learned a lot about triangles and relationships between their sides and angles. Okay, so we're going to continue that exploration. So here it says, order the sides from smallest to largest and the angles from smallest to largest. Okay, and how are these two related? So here, looking at this, what appears to be the smallest side? Side BC, the red side. Okay, so remember from geometry, you name sides with the endpoints. That's how you name a line segment. I'm sorry, my pen here is being very laggy. I'm hoping it correct itself, but let's see. Okay, so I would say side BC looks to be the shortest or the smallest. Okay, and then what? AC. So that leaves what to be the longest? Okay, so side AB. What would you call side AB since this is a right triangle? Yeah, this is the hypotenuse. So if you want to label that to kind of refresh your memory. Come on, pen. Work with me. So across from the 90-degree angle is the hypotenuse. Anytime you have a right triangle, the hypotenuse will be the longest side. Okay. What about the angles? How do you think angle C, the right angle, compares to the other two angles? It is 90 degrees, but what did somebody else say? It's the largest. Okay, it's definitely going to be bigger than the other two because it's 90. Because what do all three angles of the triangle add up to? Okay, so yeah, if you need to make a quick note of that, your triangle sum theorem that you learned in geometry is that the three angles of the triangle always add to 180 degrees. So if this one's 90 all by itself, the other two have to share the rest, the other 90. So there's no way that either of those could be bigger than the right angle. Okay, so the right angle, angle C, is definitely the largest. Okay, now what about the other two? Can you tell just by looking which one is larger or smaller? It looks like A is smaller. Okay, I think it's harder to tell looking at the angles than it was the side lengths. But what do you notice about this relationship of the order of the side lengths and the order of the angles? Say it again, Zach. Right, so angle A was not a part of side BC, right? Angle B is not a part of side AC, is it? If you look at it visually, angle A is opposite side BC. Angle B is opposite side AC. And angle C is opposite side AB. So what's happening here, what you need to remember is the rule that you learned in geometry is that opposite, the largest angle is opposite the longest side. The smallest angle is opposite the shortest side. Okay, that's a relationship between these that will always be true in all triangles, not just right triangles. Okay, so if you want to jot that down, you can. So the smallest sorry, this pen is going to drive me nuts. So the smallest angle is opposite or across from my gosh, right. The shortest side. Okay, the biggest angle or largest angle is across from the longest side, which in a right triangle, we knew the longest side is the hypotenuse. Okay. Y'all feel okay about that relationship? You remember that kind of from geometry now that we've talked about it? All right, here in this one, we have two triangles, so they're labeled triangle 1, triangle 2. It wants to know the what relationship you see between them. So let's take a look at everything that's labeled here. So I've got a blue side in both, a green side, and a red side. So those are their like corresponding sides. So they color coded it for us here. But they're not the same size, are they? Like this blue one says 5 and this one says 12.5. So they're not congruent. Okay. What about the angles? What do you notice about any of the angles? The angles are congruent. So you can see angle B in triangle 1 is exactly the same as angle B in triangle 2. Okay. Angle C is a right angle in both of them. So what does that tell you about angle A? Those are going to have to be congruent. Angle A in this one will end up being the same. It is the same as this one. If you were to calculate it, how could you calculate it? Yes. So add the two that you know and subtract from 180, and what's left, that's your angle A measurement. And you would do the exact same math in this triangle. So those would come out exactly the same. So one thing that I notice is that all 3 sets gosh, sorry, I don't know why it's being so slow. Of corresponding angles are congruent. Thank you. Come on, pen. It's going to make this take forever. Okay, so all 3 sets of corresponding angles are congruent. What else? Anything else anybody notices about the side? We know the side lengths aren't congruent, but do you notice anything? Say it again, Zach. They have a common scale factor. So if you don't remember that term from geometry, he's looking at the corresponding sides. So the 5 to the 12.5, the 4 to the 10. Okay, he's saying they have the same scale factor. What is it? What is that scale factor? He said 2.5. How did you find that? So 12.5. Oh my gosh. There we go. Divided by 5 is 2.5. It's writing my equal in the completely wrong spot. Very frustrating. Sorry. Making our notes take a lot longer. Okay, and then if I did the same thing, if I said 10 divided by 4, I actually get 2.5 there as well. Whoever's headphones are on, they're super loud. I can hear them all the way over here. You should turn those down, or probably should turn them off. I'm teaching, but we all don't need to hear what you're listening to. All right, so both of those have a 2.5 scale factor. That means that's what you are multiplying by to get from the smaller triangle to the bigger triangle. Let me draw that a little further over. So to get this missing side, I need to multiply that 3 by 2.5. So what is 3 times 2.5? 7.5. So that's your answer for number 3 here. It says in triangle 2, what's the length of the red side? That was the only missing side here. Okay, and how do you know? Okay, so I'm going to say that I found it to be 7.5. Because, gosh, I'm going to try turning this off and back on to see if it connects better or moves faster than it is. I don't know what the deal is. So because the scale factor, nope, still slow. Oh my gosh. 3 times 2.5 is 7.5. Now I'm going to scroll back up here. What does that mean? If all of the angles are congruent and there's a common scale factor between the sides, what's a word to describe those two triangles if you're telling me they have a common scale factor? Can y'all think of a word that means that? There's actually 2. One is P. Nope. And one is S. Starts with an S. No, not photosynthesis. Okay, for the P word, the second letter is R. Okay, so think about this. If yes, proportional. Okay, these are proportional. Thank you. When like think of when you make a scale model of something, or when somebody does. I don't know if you've ever made a scale model. It's if somebody says it's drawn to scale, or you make a scale model, that means that it's proportional to the life size, whatever it is, right? So like an architect makes a scale model of a building, that like what it's going to look like when it's done, and it's all going to be proportional. So every like angle will be the same, but there's a scale factor. So, you know, the ceilings may be 10 foot high in the real building, but the scale factor on your scale model, maybe that's only represented by like 5 inches or something, you know. So they figure out a scale factor to use to create a scale model or a scale drawing of things. So that's what proportional means. It means that the scale factor is the same between all of the sides. Okay, so these are proportional. So the sides are proportional. Of course, my thing won't write. Now, what is the term, the other term, the one that starts with S that I was asking if anybody knew? Yes, similar. Okay, so if your sides are proportional and your angles are congruent, then your shapes are similar. So these are similar triangles. Do y'all remember that term from geometry? So these are similar triangles. Do y'all remember you did a whole unit trying to prove triangles congruent, where y'all did like side, 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 angle, 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 side. Y'all remember that? Kind of, sort of? You may have done like a project over it too. A lot of people do a project for that unit. But what it is, this one, you're listing out the pieces, the corresponding parts of the triangles that are congruent. This one, none of the sides are, it's all angles. So this would be angle, angle, angle. That's the three parts that are congruent. That does not prove the triangle's congruent. So angle, angle, angle doesn't prove congruent triangles, but it does prove similar triangles. Okay, so these are similar triangles. Okay, which means they are proportional to each other. All right. So we're going to write those proportions, those ratios of side lengths here in this table. I'm going to first write them as a fraction, and then we'll go back and get them as decimals. Okay, but it says to write the ratio of the green to blue side in triangle 1 and triangle 2. So here the green side, I think this one was, yeah, 4 to 5. So green to blue in triangle 1 is 4 over 5. And in the triangle 2, that was 10 to 12 and a half. Okay, the red to blue ratio in the small triangle in triangle 1, red to blue is 3 to 5. And in the big one, that was 7.5 to 12.5. All right, and then the green to red in the smaller triangle is 4 to 3. And in triangle 2, the larger triangle, that is 10 to 7.5. All right, so now what are those as decimals? So if you calculate this, 4/5 is 0.8. Okay, and if in the calculator, you don't know this one probably in your head, you might have to do 10 divided by 12.5. So you can see that also comes out to 0.8. Okay, so that comes out to the same thing. Gosh, come on. This is the worst it's been lagging in a long time. All right, now if we do 3/5, that's 0.6. I'll save us time by not going back to the calculator. I'll just tell you, this also comes out to 0.6. Okay, and then 4/3, that's 1.3 repeating. So that's 1 1/3. And this also comes out to 1.3 repeating. So they're asking what you notice about the values in the table and why do you think this happens. So what you should notice, or what hopefully you notice, is that the ratios are the same for triangle 1 to triangle 2. Okay, so the ratio okay, I don't know if I can get this written down. It just keeps taking forever. So just listen to what I'm saying and make sure you get it written on yours if I can't get it all written down. Okay, so the ratio of sides in triangle 1 and triangle 2 are the same. Okay, now why do you think that happens? It happens because they're similar triangles, because the angles are congruent is why it's happening. Because if you think about this, number 6 asks us a question involving this. It says, what do you think would happen to each of those ratios, those numbers that we got, if we made angle B bigger, but kept side BC the same and kept angle C as still being a right angle? So just to give you a visual of that, so here is angle B, this size, and this is our right angle at C. Okay, we want to keep this the same length, but open this up. It's like it's opening a door wider. Okay, so I'm going to keep BC here the same length, but instead of having the door open this much, I'm going to have it open this much. See how that's a bigger opening here, a bigger angle? Okay, but we want to keep C to be a right angle, so we still want that to go straight up. Oh my gosh. So to get this to actually be a triangle, I can get my pen to draw in the right spot. So I want that to go straight up. So this is still a right angle. Those don't meet. So to get them to meet, I'm going to have to go up much higher. So you'll see how this triangle is taller. We kept BC the same length, but we opened up angle B more. So it made these two sides have to get longer. So that is the blue and the green sides had to get longer. Blue. So the blue side, BA, got longer. And the green side, oh my God. Okay, I'm done. I can't do that. That's getting too frustrating. Let me just try and type. I won't be able to draw any more pictures for you, but I can type. Okay, so the ratio of, it asks what happens to the ratios when this happens. So if you look, so blue to green, that is only going to change slightly because both of those sides got bigger, right? Want to change the size of this. So big. Okay. And then the ratio for, let's say, green to red. Was that one of them? Yeah, green to red. So that's this vertical piece to the base. So if this one is getting taller, that's the numerator, right? So if the numerator gets bigger, but the denominator doesn't change, is your number getting bigger or smaller? If you have a fraction and the numerator gets bigger, is the number going to get bigger or smaller? It's going to get bigger. If the numerator is getting bigger, which the green side is the vertical one here, okay? So because the green side is getting bigger, the green to red will get bigger because the green side increased. Now the other one was the other ratio. So we said blue to green. Oh, and that was supposed to be green to blue. Sorry. Okay, green to red. Okay, red to blue. So let's look at red to blue. If the red side is the one that stayed the same, that was the base, okay, that doesn't change. So the numerator's not changing. But the blue side, that's the hypotenuse, that got bigger. So in this fraction, the denominator's getting bigger. If you have a fraction, so let's say 1/2, and then I make the denominator bigger, so 1/4, is that a bigger or a smaller number? Smaller. So if the denominator is getting bigger, the actual ratio is getting smaller. Okay, we'll get smaller because the blue side increased. Spelled green up here. Little typo. Does that make sense? So that's our answer right there. Now, so going back to number 5, it says, what did you notice and why do you think that happened? It has to do with the angle measure. When we change the angle measure, we change the ratio. But these ratios were all the same. It's because the angle measures were the same, right? These angles were congruent, weren't they? So that's why number 5 happened. That's why the ratios are the same. It's because the angles in the triangle are the same. It's because the angles are congruent is what you would need to write. Y'all feel okay about that? All right, and then when I pass this sheet out to y'all, or when the sub passed this sheet out to y'all on Tuesday, the quick notes portion I had pre-filled in for you already. That's filled in, right? That's reviews that like SOHCAHTOA. I'll jot it down here to have on the board. Y'all remember that from geometry? SOHCAHTOA. This is sine, cosine, and tangent. And then the O, A's, and H's, that stands for opposite, adjacent, and hypotenuse. The sides of your triangle. So here it says to find sine of theta, cosine of theta, and tangent of theta. Okay, let me see if it'll let me just do some simple markings here. So here's angle theta. Okay, it's at R. Okay, opposite angle theta, that's this side. Adjacent to angle theta, that's here. And then the hypotenuse is always across from the 90, that's here. This is always going to be your step 1 when doing right triangle trig, is to label, label, label. Okay, what is the opposite, adjacent, and hypotenuse? So opposite and adjacent are the legs. Okay, opposite is on the other side of the triangle. Okay, it does not touch, the opposite side does not touch the angle. The adjacent side, adjacent means next to. So it's the leg that's next to the angle we're measuring from. It actually helps make the angle. Okay, so side TR is part of this angle, SRT. Okay, so that's the adjacent side. Okay, so once you have that, then we can try and give those ratios. This one's going to be hard to type out. I'm going to give my pen one more chance to write. So sine of theta, you can see here, when I wrote SOHCAHTOA, that's the memory trick to help you remember. Sine is O over H. And nope, my pen is not cool because that was supposed to be underlining and it wrote it above it. Come on, here we go. Okay, so O over H. So that is 12 over 13. Okay, so then cosine of theta. Okay, SOHCAHTOA tells us that cosine is A over H. So in this case, that is 5 over 13. And then tangent is O over A. So that is 12 over 5. Who's humming? Y'all, please stop being distracting. All right, so that's just setting up the ratios. Now, actually using them to solve for missing parts of your triangle, you did this in geometry again, but again, it's been a couple of years, so we're trying to see what you remember and go over it to make sure that you understand it now, even if you didn't back then. Okay, so you have 3 pieces to any trig ratio. You have an angle and you have 2 sides, the numerator and the denominator. Okay, so there's always going to be 3 pieces. You have to know 2 of them. There can only be 1 variable, 1 missing piece. Okay, so we're going to look at number 2, and we're going to label from the acute angle. So in this one, it's angle A that they've labeled 47 degrees. So from this angle, the side is opposite. This side is adjacent. And then across from the 90 is your hypotenuse. So then you have to determine, okay, what trig function, sine, cosine, or tangent, am I supposed to use to solve for that missing side? Well, obviously I have to use the missing one. That's what I'm trying to solve for. So I have to use A. And then the only other one that I know is H. They didn't give me the opposite side, so I can't use it. I can't have 2 missing pieces. I can only have 1. So I'm going to use A and H. So looking back at SOHCAHTOA, A and H, that's cosine. That's C. So I'm going to have to use cosine to solve this problem. So I'm going to write out, okay, I know that cosine of theta, okay, or whatever the angle is being called, is A over H. Now, remember, if you don't remember this is, I keep saying theta, but let me review and make sure. This symbol here, it's the circle with the line through it. Okay, that is the Greek letter theta. Okay, if you didn't realize that or remember that, I don't know, maybe y'all didn't use theta in geometry. When you do trigonometry, you're going to start to see a lot of Greek letters as variables instead of our English letters. Okay, but they do the same thing as an X or a Y or Z or S or a T. It's just a letter. It's just a variable. It's representing a missing piece. But they often, you're going to see those Greek letters more often in trig. So this is theta. It's just a circle with a line through it. So that's just the unknown. Okay, now in this particular problem, we know theta. We know the angle measure. It's labeled as 47. So we plug in what we know, which is the angle and the hypotenuse. The hypotenuse is the 3. The x is the missing piece, the adjacent side. So once you have to know 2 of these 3 pieces, which we do. We know an angle and one of the sides, and then you can solve for the missing piece. When the numerator is the missing piece, that's the easiest one to solve for. Because how would I get rid of divided by 3? I simply multiply by 3. And what I do to one side, I do to the other. So I multiply the 3 over to the other side, and that's it. Now I just type this in the calculator, and that's my answer. So in your calculator, you want to make sure that you're in the right mode, because this mode button right here next to second, this 3rd row down says radian and degree. Degree needs to be the highlighted one because we are measuring the angles of triangles in degrees. This mode, radian versus degree, only matters when you're doing trig, but that's what we're doing now. So now it matters. When you reset your calculator, when you do like that second plus 712, it goes back to radian. That's like the standard that it starts in. So you always want to check your calculator is in degree mode. On Desmos, if you're using Desmos, there's like a little toggle on the keyboard of the Desmos scientific calculator. You don't need the graphing calculator for what we're doing. I would just use the scientific. But there's a little toggle and it says RAD on one side and it says DEG on the other. That's radian and degree. So you want to make sure DEG shows if you're using the Desmos calculator. All right, so as long as you're in the right mode, then you're ready to go. We're just doing 3 cosine of 47. Anytime you hit any of the trig buttons, a parenthesis automatically opens, so you do have to be sure to close those. So approximately 2.05. Is that side length. You always want to check for realistic answers. Do my answers actually make sense? So here, does it make sense that a leg of the right triangle would be less than the hypotenuse? Yes, it does. That's a good sign. If you got something bigger than 3 as your answer, or if you got like a negative, your side length can't be negative, can it? Okay, those types of answers should like have a light bulb go off in your head, be like, hey, that doesn't make sense. Don't leave your answers if they don't make sense. Go back and check and try to find your mistake, okay? All right, in B, if I do the same thing, I label from the given acute angle, which is the 57. The 10.8 is the opposite side. This is adjacent, and this is hypotenuse. So this time they're actually asking us to find hypotenuse, and we are given opposite. So we need to see, okay, which trig function am I going to use this time? So looking here, if I want to know hypotenuse, and I'm given opposite, what trig function puts H and O together? Sine. So we're going to use sine this time. So this is sine of theta is O over H. Okay, so now the ones that I plug in, the angle is known again, it's 57. This time the opposite is known, it's 10.8, and the denominator is the unknown. Okay, so this one is not as straightforward in solving as the last one, because in the last one, you just multiplied the denominator over, multiplied that 3 over, and you were good. Here, the denominator is what we're actually looking for. So we do need to get x out of the denominator. So we're actually going to start the same way by multiplying that denominator over. So if I multiply by x on both sides, Okay, that's going to get rid of the x over here, which that's good. I wanted to do that. So I've got x times sine of 57 equals 10.8. But how can I get rid of this times sine of 57? I want to solve for x. I want x all by itself. You're going to divide because that's x times sine. So we're going to divide out the sine function. And this would be the same if it was cosine or tangent. Whatever the trig function is here is going to get divided out. So sine of 57 gets divided over, and what you do to one side, you do to the other. That is supposed to say 57. That's not very good. Okay. So that gets rid of it over here. So what you end up with, you finally get x by itself. And on the right, you've got 10.8 divided by sine of 57. So what you may notice here, what was in black to what's in black now, the x and the sine of 57, they just swapped spots, didn't they? Y'all see that? That's going to happen every time it's the denominator that's missing. So when it's the denominator that you're looking for, the denominator and the trig function switch spots. You do not have to show this work that I did in the purple and green every single time. You can go straight from this step in black to this step in black. Just show that they switch spots, and that's good enough. That's enough work, okay? But I just wanted to show you this one time so you can see why they're actually switching spots. It's because of the algebra that we're doing to solve for x. Okay, but now it's just a calculator question. So I go and I say 10.8 divided by sine of 57. Okay, and so that's approximately 12.88. For that one. And does that make sense? It's the hypotenuse. Should it be bigger than the leg? It should. Okay, so that one makes sense again. So you check for the realisticness, does your answer actually make sense? Okay, now in number 3, this is just a multiple choice. They're saying which one of these could represent tangent of A is 5/3. So remember, what's the tangent ratio? Opposite over adjacent. So what they're telling you here is that 5 is the opposite and 3 is the adjacent. So they're saying, I'm going to go, gosh. Y'all are probably too young to have seen Office Space, but I'm feeling like I want to take this to a field and beat it with a bat. It's been very frustrating. Okay. So what we're looking at here is from angle A, because it says tangent of A, this would be the opposite and this would be the adjacent. Does this look like this picture would represent the O being a 5 and the A being a 3? No. This picture, O looks smaller. O needs to be bigger because 5 is bigger than 3. So A does not look like it could represent that. What about B? So opposite of this angle would be the opposite, and this would be the adjacent. This one looks like it's shorter as well, doesn't it? So that doesn't look like it would be a good representation of that. Okay, and then in C, here's the angle A. So this would be the opposite side and the adjacent side. Does this one finally look like the opposite side's bigger? Yes. So that looks like it could represent tangent of A being 5/3. So that looks like a good answer. So let's see why D is wrong. So from angle A, this would be opposite and adjacent. What do those tick marks mean? Do y'all remember in geometry what that means? That means they're the same. That means those are congruent markings. So there's no way that this could be it because 5 and 3 are not the same number. Okay, this is an isosceles triangle, and if tangent of an angle is 5/3, the sides are not the same. Okay, so that one is out. That's why it was C. We're going to skip 4. Y'all don't need to be able to explain that, so I'm not going to take the time to go through it because it's not needed. So last but not least, we've got sine of theta. So here's our theta. So this is opposite, adjacent, and hypotenuse, is 0.75. Give a set of possible values for these lengths of those sides, and they call them A, B, and C here, that would make this true, make this sine ratio true. Well, what is 0.75 as a fraction? It's 3/4. So the easiest one to do, oh my gosh, please write, is 3/4. To say, okay, 0.75, you could get that by doing 3 divided by 4. Okay, so they're saying that's the opposite and the hypotenuse. So you could label that and say, okay, the opposite side is 3, the hypotenuse is 4. How could you find the third side if you know two sides of a right triangle? Pythagorean theorem. So you could do a squared plus b squared equals c squared. Okay, remember c is always the hypotenuse. Okay, so that means that I would have a squared plus 3 squared equals 4 squared. And that would be 9 and 16. And what would I have to do to solve for a? What do I have to do? I have to get a by itself. So right now it's a squared plus 9 equals 16. So I'm going to subtract the 9 over. Okay, to get rid of it on the left. So then I've got a squared equals 7. All right, y'all go ahead and go to lunch. I'm gonna finish this video because I'm recording it. But when you come back from lunch, I'll finish it with you. Got a squared equals 7. Okay, and then to get rid of the square, you have to take the square root. So you end up with a is the square root of 7. So that is this missing side over here. So that is one possible set of values for A, B, and C. A being square root of 7, B being 3, and C being 4. The other possibilities, there's infinitely many possibilities, but it's anything that would make the OH ratio 0.75. So really you could have done 6 to 8 because that would reduce to 3/4. Or you could have done please work. You could have gone even bigger. You could have said 9 to 12. Okay, or 12 to 15. Okay, hopefully you get the gist of that. Any ratio that would reduce to 3/4, or that when you divide in the calculator would give you 0.75 would have worked. And then you could have used those side lengths in your Pythagorean theorem, and that would have changed this A slightly. If you had done the 6/8, these are twice as big, this would be twice as big. So it'd be 2√7. Okay, or if you had done 9/12, that's 3 times as big. So this would have been 3√7 to keep that proportionality. But that's it. So that's the end of that sheet. And we're going to take the official notes tomorrow.